So in this talk, I'll be talking about, like, again, this is just a motivation. So I've given an introduction. In the rest of the talk, I'll be talking about a system for processing big geospatial data, which is called GeoSpark. We developed at ASU. The other part of the talk, I'll be talking about a system that trades the analysis accuracy for scalability and interactivity, because this is something needed. We want scalability, we want interactivity. I will talk a little bit about other projects, and then I'm going to talk about future directions at the end as well. So first, let's start with GeoSpark. So before I talk about GeoSpark, I'll just give an overview of Apache Spark back then, before we developed GeoSpark. How was it? So Apache Spark, back when we started working on the GeoSpark project, it was starting as a scalable data processing system that anybody can use to do their data processing task at scale. So, and the problem with it back then is that we looked at it and we said, okay, let's use it to do geospatial data processing. But we took it and looked at it, we tried to develop. The problem is that Apache Spark did not provide a geospatial data processing API. So this was similar, for example, back then when people invented database systems like, for example, Postgres, and did not have, back in the time, did not have a data processing API. So usually when you don't have a data processing API within the system itself, that means if you're developing geospatial applications, you have to treat geospatial application, the attribute, as a yet another attribute. And yet another attribute here, a lot of people kind of look at geospatial data as just two extra columns, X and Y, longitude and latitude, and that's it, which is far from what geospatial is. This is just one type of geospatial data, longitude, latitude, or X and Y coordinates. And also a big problem is that even if you can implement as a programmer the geospatial application within Apache Spark, right, then you have to write thousands of lines of code to implement just simple operations like spatial join, for example. So that was a problem. And let's say that we have a very smart application developer who's going to take Apache Spark and implement geospatial data, and she's willing to write thousands of lines of code to do that. The problem with this is that it could not efficiently optimize these geospatial queries. It would be very difficult for this programmer to optimize the code for geospatial queries. Why? Because within Apache Spark itself, it didn't have the notion of spatial proximity aware load balancing, no spatial indices, no spatial data compression techniques, which are really, really necessary, especially if you're running data processing in a cluster. So all of that was Apache Spark back then. So Apache Spark was great for traditional data processing, but when doing geospatial data, it will work, but it will not be it will not be optimized. It will take forever to run, for example, geospatial data processing tasks, which is something we don't want. So having said that, so we took it as a challenge to implement, to take the core engine of Apache Spark and shake it and make it work with geospatial data. And we developed a system called GeoSpark. So GeoSpark, from a very simple, kind of perspective, it allows the data scientist to load geospatial data from the traditional formats they're used to. For example, from Esri shapefiles, from the traditional shapefiles, GeoJSON, NASA format, from PostGIS, for example. So these are the regular ways that people are used to load geospatial data from. And it can be automatically loaded into a cluster of machines, because this is the core of Apache Spark itself. It's a cluster of machines. On top of that, the data scientist can write geospatial data processing tasks. And this will include geospatial, like geometrical operations, can include spatial queries that people are used to, and they can build programs that can actually use these spatial operations as building blocks to do the spatial analysis later. So this is what, from a higher perspective, what GeoSpark is. So for example, like GeoSpark also allows the application developer to write the spatial data processing task using SQL. So it has a spatial SQL API, and some of you may be familiar with the spatial SQL API. that if you've used PostGIS before. So we implemented the same standards, which is again the Open Geospatial Consortium standard and the MM3 standard within GeoSpark itself. So you can do a spatial join, for example, if you want. You have these two tables. One table has the Google Places, the other one has the New York City taxi trips, and you want to find all the trips within a 10 meters distance from a hospital. So you can do a spatial join like that. And the spatial join here, it's a spatial join because it actually tests for the distance between two locations in two different tables. This is just one example of what it can do. So the data scientist will write the spatial SQL to do this task, and then retrieve the data, maybe do something else with it. So within GeoSpark itself, it has this layered architecture. So you have, again, down there, you have the data loaded into what we call the Spatial Resilient Distributed Dataset layer. So SpatialRDD, or the SpatialRDD, is basically a data structure that is loaded and distributed across the cluster. And it's like every SpatialRDD partition exists on a machine in the cluster. And these SpatialRDDs represent the spatial data, the spatial objects. We have different subtypes of the SpatialRDDs. Like, for example, you have a point RDD in case the geospatial data you have is a point data. We have a polygon RDD, we have rectangle RDD, and so on and so forth. We implemented different types, all the different types of geospatial data that can be loaded into the cluster. Most importantly, on top of all of this, like, again, once you implement these point, polygon, rectangle RDD, the programmer can actually use these RDDs to do spatial operations. And it comes with a suite of geometrical transformations and actions on these kind of objects. And it can also decide whether to automatically build spatial indices on the local partitions. And also a very important feature of the SpatialRDD layer is that it can also partition the spatial objects in the cluster based on the spatial proximity. So this is what the SpatialRDD is. On top of the SpatialRDD layer, there's a spatial query processing and optimization layer. So the user will write the spatial SQL API. Again, the optimization layer will optimize the code for the Apache Spark cluster. So Apache Spark has certain ways to run run jobs within a cluster. So the optimization layer will optimize the spatial SQL queries based on Apache Spark and also based on the characteristics of the spatial data. And we have several implementations for spatial range operators, spatial KNN operators, spatial join operators, like in-house. So, and not only that, also the data scientist can plug in, or the user can plug in new implementations for these new operations. So the SpatialRDD, the memory structure looks like this. So we have a very compact in-memory representation for the spatial objects, and it's unique. It's a unified representation for all types of spatial objects. And it depends on it, the bits and bytes that you can fill in within this, the memory representation, it differ. So we have for the point RDD, it fills in the bytes within this kind of memory representation differently than the polygon RDD. So the idea here is that we can support these heterogeneous spatial data types within the same RDD, which is something that Apache Spark didn't do before. And this will help definitely with the implementation of heterogeneous also applications on top of that, spatial applications. The SpatialRDD, as I said before, it can be partitioned based on the spatial proximity of spatial objects. And this concept existed already before, but we actually developed that within the core engine of Apache Spark itself. So what we did is that we have an algorithm that can sample the spatial objects within a SpatialRDD in the cluster, and then we can build different partitioning techniques. And we implemented these are just examples here, but we implemented like maybe 6 or 7 spatial partitioning techniques. One of them is a traditional uniform grid, KD tree-based partitioning, quad tree-based, and R tree-based. So you can choose, the data scientist can choose, or the data scientist can ask GeoSpark to automatically choose the partitioning technique for it. So we take the leaf nodes of these partitioning trees, and we use them as the global partition file, and this is stored in the master node, and then repartition the RDD according to the partition file. This is how it's done within Apache Spark itself. It's done in 2 stages. So the first stage, you have an RDD that is not partitioned, and then you have to go through what we call like a Y transformation to do the partitioning, but you do it only one time, even though it's expensive. You do it one time, and then you benefit from the spatial proximity-based partitioning, because many of the spatial queries and spatial applications will benefit from that. For indexing, the spatial RDD also, there are indexing that exists there. So there is one type of index called the global index. The other one is called the local index. So the global index, you build basically a bounding box of each spatial RDD partition. And it's lightweight and stored on the master machine. It's used for partition elimination in case some of the partition will not contribute to the spatial processing tasks. And there are no entries for individual records here. For the local indexing basically is that for each spatial RDD partition, we can build a local index on the machine of this spatial RDD. And the local index can be traditional index, spatial index, like for example, R-tree, quad-tree, or so many of the others. We allow also the user to change the index based on whatever application they have. The idea of having the local index is to minimize the amount of local computation for all the partitions running, even though you have a parallelized kind of like workload across a cluster, but you want to minimize the work that each machine is working on. For the global index, it's used for basically partition elimination, because you don't want partitions to work on something that they're not contributing to the final answer. So it's used for that. So after you have the spatial RDD, we said there is a spatial query processing layer. Again, we implemented so many of these spatial query processing operators that can run efficiently on top of the spatial RDD layer. I'm not going to talk about each of the implementations, but I'm going to talk about just one algorithm, which is the one spatial join operator that we implement. So one version of the spatial join operator, at first, you have 2 RDDs. Let's assume you have GPS points and state boundaries, and you want to join the 2 RDDs based on, you want to return every GPS point within a state boundary. So first you do a zip partition, and this zip partition step will basically zip all the co-partitions from the state boundary and the GPS point together. So the assumption here is that the spatial RDD, the 2 spatial RDDs are co-partitioned based on the location of the state boundary and the GPS points. So you zip them together into one RDD, and then you apply a local join. And the local join here can use can be an index nested loop join if there is an index on the GPS points, for example, a spatial index. After that, a very important step is the duplicate removal. So the idea of having, since we did this partitioning can introduce duplicates across multiple machines in the cluster, across multiple partitions in the spatial RDD. So that means the answer can be replicated on multiple partitions. In that case, you want to remove these duplicates. So we have a duplicate removal also step that uses the reference point, which is, again, a technique that is well known in the well known before, but we implemented it in our system as well. Once you do that, you have the spatial join results after doing these 3 steps. And since it relies on co-partition data and spatial indices, the result can be way faster than doing this on the bare metal Apache Spark without using GeoSpark. So this is how it works within Spark itself, the stages of how it works. Since it's co-partition, you have narrow dependency all the way now down from the 3 steps you have. And narrow dependency in Apache Spark means that there is not a lot of data shuffle across the cluster. And the reason we have narrow dependency all the way down is that we kind of squeezed every step of the process in GeoSpark to make sure that we avoid data shuffle across the cluster, which is, again, very important, especially if you have large-scale data. For the spatial SQL optimization, so we implemented.
Mohammed, sorry to interrupt you, but I think there's a question. Maybe you can pause a little bit to take some questions.
There is a question. Yes, please.
Yeah. So I mean, slightly more general question. How Because the Apache Spark is always evolving. So the GeoSpark, how does it keep pace with it?
That's a great question. We are actually some of the things we implemented uh, are pluggable in a sense that you don't need to um, all the time update the code of Spark itself to match whatever we have in GeoSpark. So similar to PostGIS, for example. So PostGIS, what happens is that it's an extension to to Postgres. So you just have to implement, like, to load in or plug in the extension, or say I want to use this extension, and it will work. So many of the functionalities that we implement are that way, are pluggable in that easy way. Some of the very hardcore optimizations that we implemented, we need to modify the code with every version of Apache Spark. And the reason behind this is that, again, it's hacking the core of Apache Spark itself. And the core of Apache Spark keeps changing, as you mentioned. Some of them, but not a lot. So we try to be modular as much as we can so that we can keep up with the new versions that come out of Apache Spark every once in a while. And we've been successful so far in that sense. So we have we keep two versions. The version that we have public on GitHub that I will be talking about in a couple slides. This is the version that is pluggable, which means that with every version of Apache Spark that comes out, our GeoSpark will work with normally, and we always keep it clean, and we always keep it up to date with the Apache Spark new version. But we have another version that we don't share. We don't share on GitHub or for free or something like this. Is a very much more optimized version that hacks the core engine. But this is a different story.
The other just question I had: how do you deal with skewness? Because space is very zip codes in East Coast and West Coast are more concentrated than the Midwest of the US. And you have to query. So when you do the spatial partitioning and data structure, how do you deal with that? At least in Apache.
Yes, this is a great question too. So for the skewness in geospatial data, Spark, GeoSpark is actually is implemented to take care of of this problem as well. And the way we take care of it is that we use the spatial partitioning that we talked about, and it's spatial proximity-based partitioning. The idea, yes, I know that so there are so many partitioning techniques that exist out there. So what we did is that to do the partitioning itself, if you want to partition the data, if you want to learn the distribution of the data first before you do the partitioning,
right.
That's an expensive kind of operation, the real distribution of data. So what we do is that we use a sampling technique, which is that practitioners use generally speaking whenever they do these kind of operations. So we sample the RDD first, and the RDD again can be terabytes of data. That's okay. We're just going to get a small sample of it, and we determine based on the distribution of the data, the spatial distribution of the data, we determine the boundaries of the partitions accordingly. So the idea here is that based on the sample, we decide the boundaries, and then we use these boundaries to partition the original data, which is again terabytes. In that case, we make sure that we have load balancing across the cluster, which will load balancing is the most important thing that we get from. So the skewness problem, if we have data skew and this skew is introduced within the partitioning itself, it can lead to a huge problem when we try to load balance. But we don't have this problem in GeoSpark because we do that. We do the spatial partitioning.
I see.
Is that clear?
Yeah, I get some ideas. Thank you.
Thank you. So, actually, we've tried. We've done a lot of experiments on data that is skewed, uniform, and all these kind of things on different partitioning techniques we have with GeoSpark, and we show actually superiority in terms of performance and load balancing compared to other systems as well. and most importantly, compared to Spark itself, because people that are using Spark, we tell them if you don't use GeoSpark, you don't have a balanced load if the data is skewed. And in that case, you can spend the task that you're going to run in 10 minutes, for example, with GeoSpark, it's going to take 10 hours with the regular Spark, without GeoSpark. So yeah, so this is basically the idea. So we also, I'm going to skip over this real quick here. So spatial SQL optimization, we have an optimization layer on top of all of that. So we have the operators, we have the SpatialRDD, we have the data that is partitioned now. We have a SQL query that comes to you using the traditional spatial SQL that people running spatial queries are familiar with. So we also decide which operators to use and which physical plan to run within Spark based, again, on the distribution of data in Spark, based on the Spark DAG scheduler, based on the Spark wide and narrow transformation that exists out there, and also based on the spatial distributions and the spatial data statistics, like, again, PostGIS does, for example. So we take all of that, we have optimization algorithms that decide that. So I'm not going to the details here since I want to also talk about other things. But this is actually, for example, two plans that you may choose. One of them uses the broadcast join within Spark, and the other one using a range join. This is two different operators that we can actually choose from based on the cost. And GeoSpark automatically chooses that for you. Before, Apache Spark had an optimizer, but couldn't take into account the geospatial aspect. So it will not know which spatial join operation is better than the other, given the circumstances, given the data distribution. So now it can, using GeoSpark. So this is just a summary, because a lot of people say, okay, how much is the performance difference that you can give us? Because this question makes sense. So GeoSpark can perform spatial join on 3 billion GPS point data and 200,000 polygon data in about 3 minutes on 4 commodity machines. There are more details for sure for this, but I'm just giving you an idea of how good it is when it comes to performance. When I say 4 commodity machines, these are machines that my students are using in their lab. There's personal computers. It's not even a server or anything like that. And it runs on this big data set and spatial join operation in 3 minutes. Something that Spark itself, when we run it on Spark, on the same machines and everything like, and all of this, it took about 16 hours to run the same operations in Spark. So that's a really great benefit for somebody who wants interactive and wants scalable analytics on top of the spatial data. So I already talked about this. I'm just going to quickly talk about it. So we didn't only do the research and implemented a prototype. We implemented a very mature prototype of the system that is used in production by other companies and other people, either in industry or academia. So GeoSpark is a system. You can, there is the link for it is in here. I recommend that you guys, all of you, either now or after this meeting, please go take a look, download and play with the code. It's not just, again, a bunch of code that we throw on GitHub. No, it's actually very clean, and it's used in production by some of these companies that you can see here, and is being downloaded like constantly, more than 10,000 times a month. So there is use for it. There is a huge benefit if you have spatial data to use the system. I recommend that you please give it a try. Also, I'm not again, I can't self-endorse or myself for forever, but there is this paper in VLDB 2018 that is not by us, by other group from TUM, and they compared so many spatial analysis tools and their scalability and efficiency. And here's what I'm quoting what they say about GeoSpark. They say GeoSpark comes close to a complete spatial analytics system. It also exhibits the best performance in most cases. And again, they did that benchmark, and it's totally not us. It's a totally different team, and it's a very respectable team. So please give it a shot. So now I'm going to move to talk about, again, before I move to talk about something else, GeoSpark as an ecosystem, we implemented so many things with it and so many extensions to it to support different applications. So we have an extension that supports trajectories and mobility data. temporal data. We have a Python API in case you're a Python developer, if you want to do the analysis using Python. We have a spatial now, one of my students is working on a spatial streaming API when you have streaming data. Another API we implement on top of it is geosimulation, if you have road network traffic simulations. So we have a huge extension actually of how to do the simulation at scale with GeoSpark. So we have to extend GeoSpark to do that. So, and we're adding new functionality constantly. So every couple of months we add something new and we release a new release for the system. So this is just to give you an overview. So now that we talked about GeoSpark, I'm gonna just switch gear talk about a different system. However, it's under the same umbrella of how can you make the data science task more scalable and interactive. So going back to this figure that we already talked about, so we were talking about, okay, data processing and preparation and retrieval, it can be extremely slow. This is true, but you can use a system like a scalable system like GeoSpark, for instance, to do the data processing and preparation at scale. So we said, like, again, the spatial join, for example, can run in 3 minutes. And if you have smaller data or more machines, you can even run it way faster than that. So you can scale and get things fast. However, the result of the join itself or the result of the query can be very large still, can be still gigabytes or even terabytes of data because the data is large. So you reduce the size of the data using a query, but again, the result is big. So that will bring us to the second problem, which is again, running data analysis, which is again, a simple Python script or running Tableau, building a heat map or a visualization dashboard using Tableau, for instance, on gigabytes or terabytes of data, it's not gonna work. So the data itself is huge. So running this, it will crash. These applications will crash because the data is so big for them to handle. So how can we solve this problem? So again, looking at the problem in more details, this is a visualization dashboard, as you can see on the left-hand side of the slide. It's a visualization dashboard built on New York City taxi data, and it visualized the data on a heat map using Tableau. On the right pane here, there are so many filters that you can filter the data and redo the visualization. So what happens is that, for example, you might say, instead of visualizing everything, all the taxi trips in New York City, you may want to redo the analysis by, for example, checking for people, taxi trips that have been paid for using credit card instead of everything, or using cash, or you only want to do the heat map for all the trips with passengers, 5 passengers or 4 or something like this. So the idea of the analysis, it's an iterative analysis, and to get the insights, you always doing the filter and then redoing the heat map, doing the filter and redoing to get some insights of how the data looks like. So this is very mainstream. So a data scientist usually do that when they do the visualization, when doing this visualization. So here, for every single filter, you need to go back to the system itself, the data system, run the query, get the new data, because again, it's not the same data when you do the filter on, and then draw the heat map on. And then for a new filter or a new set of filters, you go and retrieve new data because it's a new query, it retrieves new data, and then you show it. So you're always doing this in an iterative manner. So how can you make this more efficient? So obviously, if the data is too large, every single step will take a while before you can generate this heat map. This heat map will not appear instantly as it appears here in this video. So one way to make this more efficient is instead of returning the entire result of the query every time, you return just a sample. So the query will run, instead of returning 10 gigabytes as the result of the query, you return a sample of the result, which is just 100 megabytes. Why is that? Because this sample is small. Tableau can visualize this very fast, as opposed to 10 gigabytes. So people have been using sampling. So these are the different strawman like techniques to do the sampling. So you have, first is the no sample approach. So again, this is the approach that is actually very slow, but it returns a lot of data. The second approach is called the sample first approach. And the sample first approach is basically, it builds a sample of the entire data set that we have in the database and run the queries on the sample and return the result based on the queries on the sample. So this will be very fast and return again small sample. However, it has a problem because sampling the entire database, you lose a lot of patterns, important patterns that might be important. So as you can see, there is a hotspot here that this approach missed, this red circle. A third approach is a sample on the fly approach. So sample on the fly approach, you run the SQL query, and then the result, you sample the result and then return it. So here you sample the result of every query. This is a very accurate approach in a sense that you only sample the result of every query. However, it still takes a lot of time because the sample is small, which is great. This is what we want. But running the query and do the sampling after the running the query, it's also another delay that you add here. So there are so many approaches that existed that use stratified sampling. So for example, in the Sigma community and VLDB community, there have been a lot of approaches that create and materialize stratified samples in advance and use them when necessary. So the problem with these approaches that existed back then is that they provide statistical guarantees for OLAP type queries. So the queries that are running are some average count, something like OLAP analytics, and none of them worked on spatial data or spatial analytics or spatial visualization, for example. So that is a problem. Another thing is that they provide statistical guarantees. Statistical guarantee means here that there is an error bound, which is understandable because you do sampling, but the error bound has a confidence interval. It's not a deterministic error bound, which can be confusing for some of the, for some data scientists. So what we did is that we implemented a middleware system called Tabula. Tabula is, again, you have the visualization dashboard here, you have the data system, similar system architecture, except that we, in the middle between the data system and the visualization dashboard, we have a framework called Tabula. Tabula takes the query from the visualization dashboard and rewrite it and into the data system to retrieve a sample and then return the sample to the user. How does it work? This is the magic here. So let's see how it works. So Tabula, you have data scientist. First, you have to initialize the system itself, the Tabula middleware system. So whenever the data scientist create an initialization query, so Tabula, what it will do, it will look at the data and it will build what we call the materialized sampling cube. So the materialized sampling cube is basically creates sample for every single unforeseen query that may come in the future. And it makes sure that the sample retrieved, the analysis that you run on it, will return result that is within a specific accuracy loss threshold specified by the data scientist itself. So the data scientist will say, you know what, I'm running visualization on top of that, I'm building heat maps. My accuracy loss function is X, and the accuracy loss threshold I have is that the heat map that you generate must be not too far from the heat map that on the sample by this amount. So the data scientists define that and plug in these kind of thresholds and functions within the sampling cube initialization module. The system will take that and automatically generate these samples for different attributes, as you can see on the data. And these attributes will be used as the filters later. So after that, when the user, now comes the query time, whenever a query runs through the visualization dashboards, it goes through the sampling cube query processor, and this will rewrite the query to, instead of accessing the data, it will access the sampling cube itself. And the sampling cube will retrieve a sample from the sampling cube and then return it to Tableau, for example, to do, this sample will be used to build the heat map, and so on and so forth. This goes into many iterations. Again, the initialization query looks like this. It's similar to creating a table using which exists in many data systems. And you have to define the loss function, and you have to define the sampling or the accuracy loss threshold here, which is the theta sampling threshold. Once you create that, so this is just all the lines of code the user has to create, has to initialize, and then this will automatically generate the sampling cube we talked about. The user-defined accuracy loss function, it's not something we define. The user has to specify that. And the reason behind this is that an accuracy loss function differ based on the analysis you're running. If you're building heat maps, it's going to be different from running regression analysis. It's going to be different from building cartograms. So the data scientist, we give the control to the data scientist because the data scientist knows what she's doing. And the accuracy loss threshold is also something that the data scientist has to be acceptable to the data scientist. So the data scientist, you know what, I'm okay with 80% accuracy. So based on that, we're going to build a sampling cube. If the data scientist said, I'm okay with 95% accuracy, we're also going to build a sampling cube accordingly. So again, the queries work like this. This is the original query. You're selecting taxi trips for that are paid for in cash and has number of passengers between 0 and 5. So we rewrite that into the sampling queue. So this is just a very simple query rewriting rule here, and so on. So you keep asking queries and we rewrite them to retrieve the sample, and so on and so forth. So the problem with the sampling cube that we figured is that, yes, it returns a sample and every sample has a deterministic accuracy or deterministic error bound for the accuracy. However, the problem with this is that it's a huge cube, because if you want to build a sample for each possible unforeseen query, it can grow really, really fast. It can be bigger than the data itself, which is something that will make the system not scalable. So what we did here is that we build a partially materialized sampling cube. And we selectively select cells in this sampling cube that will that we say will always return a good query answer that will satisfy the accuracy loss threshold specified by the data scientist. And for some other sampling cubes, we don't materialize because we know that we can just use the global sample and it will return a good answer already. Another technique we have is also we shrink the size of the sampling cube even more by selecting a set of representative samples that can be used to represent other samples. For example, you can have sample 1 can represent sample 1 can represent sample 2, 3, and 4. How can it represent that? Because if you run the analysis on sample 1, it will return pretty much the same results, or results within the same error bound that sample 2 returns. So we can use it instead. So this is why we don't materialize everything. So the idea here is that we have a sampling graph, sample representation graph, and this graph we kind of go and select a minimum set of samples. And again, this is an NP-hard problem, but we have a greedy algorithm that can select the minimum set of samples to be materialized. So to give you an idea of how this performs, we implemented this middleware system called Tabula, and then we tested the performance on real visualization dashboards, and we compared it with so many other techniques. The state-of-the-art technique that was published on spatial sampling was published in SIGMOD in 2017. It's called POISM. So this one also returns a sample. However, it does not have the deterministic accuracy bound, and also it does the sample on the fly. As you can see here, we can achieve way better performance in terms of the data system time. So it takes the system to return the sample itself. And the query time here is 200 milliseconds. The visualization time itself for the visualization dashboard is 300 milliseconds. If you combine both of them together, this is very interactive from the human perspective. So we can achieve interactivity and still achieve the accuracy by the end user, specified by the data scientist. So this part, I conclude this part now. I'm just going to talk quickly about other projects real quick. And again, I'm going to talk about future directions. So we've talked about this again. I'm bringing this big picture again and again so that we all know what this is about. So we talked about the data scale here. So we can reduce the data scale not necessarily by sampling. We can reduce the data scale by running smaller range queries on the data and doing the data on smaller ranges of the data itself instead of the entire data set. So running range queries on the data, this is to speed up range queries in general. People have been using in database systems, been using indices for a while. So these indices can be B tree, can be R tree in terms of spatial data, for example. Very efficient indices that return the result very fast, and again return the necessary amount of data for within the range itself. So what we did is that we looked at this problem and we said that R tree is great, B tree is great in terms of speed of the query, which is something really needed. However, if you have massive amount of data and you want to build many secondary indices on the same data set, these indices, these index structures like the R tree and the B tree do not scale because they consume a lot of storage or memory footprint, usually between 15% and 25% of the size of the original data, which is huge if you have terabytes of data and you build multiple secondary indices. And most importantly, these indices, they take forever to update. If you have a lot of updates, which is again which exist in so many applications these days. For example, if you have taxi trips, if you have Uber trips or something like this, data is being constantly added, inserted into the system. So how can you do this also at scale with having these indices? So what we did is that we built we build an index that gets rid of the overhead, storage overhead, by not indexing every entry in pages, like happens in R trees or B trees. So we removed all of this, and we had a flat structure so that we can have faster updates and we have also less memory footprint, while still having a fast comparative. It's not going to be as fast as the B tree and R tree for all queries, but it's comparative query performance compared to R tree and B tree. And this is an indexing scheme that we built called Hippo. So I'm not going to cover the details of Hippo, but just to remember it was something. So you have very small storage footprint, low maintenance overhead, and on the other hand, you have comparable query performance, nearly as fast as a B tree and R tree for medium selectivity queries. Medium selectivity is like the query is selective, but it's not selective that it returns only one record or 10 records out of billions of records. It works for analytics applications that still returns a big bunch of data, but it's still selective compared to the entire size of the data. So this is what this project is about. Another project also that we've been working on is also how to support spatial data, process spatial data in graph database systems. So there are so many in graphs in general, so many graphs that have spatial attributes. An example of that is the Wikidata knowledge graph. It has between 12% to 30% of entities in this graph have spatial attributes or geospatial in nature. And there are so many other graphs that have spatial data, like again, social graphs and epidemic networks and brain simulations. All of them, they're graphs and have spatial and spatial temporal information. So what we did is that we again built a prototype of a system called Spindra, and Spindra basically it incorporates the location awareness within the graph storage and indexing layer and the graph query processing and optimization layer. So you have a graph database. We allow you to write graph queries that have spatial predicts as well, and we co-optimize the graph processing and the spatial processing within the graph database system itself. So this is basically the main idea behind Spindra.
5 minutes more.
Yes, I'm almost done. Yeah. So back in my PhD, I also worked on recommender systems and how can you support location awareness within recommender systems. So this is also some work that I'm really proud of. For the future, so there are so many things I want to do in the future. So one thing one aspect is democratizing spatial data science. So here is that we looked at GeoSpark, we looked at so many of these systems. However, I want to allow users to write data science tasks in their preferred language using their preferred tools. Can be GeoPandas, R, or any of the existing tools they have. And these tools may not be in a distributed system, but I want to take that code, compile it into GeoSpark program that can scale in a cluster on the data itself. So this is one research. It's actually a very hard thing to build this compiler. Another thing is also spatial data cleaning and integration. There are so many work on data integration out there, but very few of this work that actually focus on the spatial aspect of the data. which there are a lot of challenges and a lot of opportunities also here. Also, another thing that I'm actually focusing on these days is building spatial and spatiotemporal machine learning systems. So existing systems like TensorFlow, PyTorch, and scikit-learn, they do not provide support for geospatial data. So we want to be able to do that. And again, there are so many challenges to doing this. We are actually investigating the opportunity to do that. Another thing is that also I want to focus on optimizing spatial data processing for specific domains. So usually when we build our systems, we always claim it's very generic for any types of geospatial data. However, when we look at details, we think that we can even optimize it even more for specific applications like epidemiology, neuroscience, transportation. There are so many kind of details, nuances that we can actually work on. Also, another thing that we're working on, that's a continuation to what we've been working on, is a system support for human-in-the-loop data analytics. So again, this includes geospatial visual analytics. How can we always design the system knowing that the human is in the loop? Even machine learning system, how can you also design the system itself with the human in the loop kind of constraint or assumption? All these kind of things we're working on as well. Another thing, a future project or that I started working on already is system support for the Internet of Things. So we're all familiar with the Internet of Things. There are so many opportunities with it, is that every piece of data generated from the IoT, again, these devices that are deployed ubiquitously, they generate spatial and spatiotemporal data because, again, they sense the environment, the physical environment. There are a lot of problems with this, a lot of challenges that can happen, is that there is heterogeneity is crazy when it comes to the Internet of Things. So the IoT devices have different software and hardware capabilities, and how can you build a system that integrate all of that together? Shall we process the data on the device, on the edge, or in the cloud? Each device generate different physical measurements, like again, one generate measurements, temperature, LiDAR, humidity. You can have another one, the traffic cams. So how can you integrate data together? So all these kind of heterogeneity issues, how can we build a system to do that? So this is one aspect that I'm also focusing on these days. And all of this has to run. You need one system that can run signal processing, machine learning, as well as spatial and spatiotemporal data management, all in one system. So you want to allow all of this in one system, co-optimized in one system. Another issue is privacy. Obviously, I'm not working on that right now, but I think it never gets old working on this topic in general when it comes to, especially when it comes to IoT and devices that are deployed in the wild in general. So this is one aspect. It's called Data Science for Cities Initiative, and this is pretty much the last thing I'm going to be talking about. So this is basically related to my NSF Career Award. So we're trying to build this initiative that building data science tools that help people build applications that benefit cities. And again, for educational activities involving citizens in the cities and collaboration network across multiple domain experts. So this is one initiative. There are so many details to it. I'm just giving you an idea of something that I'm doing. And this is building on the science we're doing. It's mostly an educational initiative. Also, we're planning, hopefully, we're in the early stages of doing a spatial data science book. So the co-author list is still like, we're still building it. We're still building the table of contents, but this is years from now. But hopefully you will see that in a couple of years or something.
Excellent.
Yeah, so last thing is that I just want to thank my students, actually. They've done all the work, right? I was just there advising them, so I would like to thank them a lot. There are so many also undergraduate and honor students that are not listed here. Thank my collaborators, current and the past. I also acknowledge like NSF and other funding entities that provide support to us. This is just a take-home message. So spatial data science treats location, distance, and spatial interaction as core aspects of the data science pipeline. GeoSpark enables spatial data processing at scale. Tabula is a middleware system that allows data scientists to trade accuracy for scalability and interactivity. Scalability, seamless interaction, and human-in-the-loop approach are key factors in democratizing data science in general and spatial data science in particular. So by that, I conclude my talk. Thank you so much for listening. And if you have any questions, I would love to take it.
Great, thank you very much. So there are a few questions. Let me just quickly go through them.
Please.
One was, again, related to the partitioning in GeoSpark. If objects are small, they can easily be partitioned. How do you process large objects? Do you put them in several partitions? Let's say we have a line that goes through several spatial partitions. Do you keep replicas while partitioning, or you break up the line and keep a piece per partition?
If the line, let's assume the line is so big that it cannot fit on one machine, yes, we partition it. We put it on multiple partitions. However, we try to minimize these instances as much as we can. So the idea here is to try to make the spatial object fit in one partition as much as we can. So in other words, so the partitioning technique will favor moving other objects altogether to other partitions instead of partitioning the single object itself across machines.
The other question was slightly even higher level. More higher level. You can give a short answer. What's the difference between spatial SQL and regular SQL?
That's a great question. So spatial, like SQL, SQL is regular SQL, but with spatial constructs and spatial syntax with it. So it's basically spatial SQL that implements the MM3 and the, for example, OGC standard, which contains the geometrical operations, something like ST within, STD within, ST contains all these kind of traditional, not traditional, but all these functionalities that are implemented, for example, in Postgres. So it adds to the standard. It has the SQL standard, but it adds to the standard these kind of spatial constructs in the language itself.
Okay. And the second last question, I have one question of my own. What would be the part of on GeoSpark that makes the most difference when it comes to performance? So what's the key thing that really makes GeoSpark shine?
If I have to kind of rank them, I would say it's the spatial partitioning. This is number one. The second one is the optimization itself, the query optimization. So this is in order. These are the two things. The third thing is also the compact representation of the spatial objects, because this makes a huge difference, especially if you move data around in the cluster. If you move 10 times less the size of the data, it will be very efficient for running the task.
Finally, you can't avoid this question. Are you doing anything with COVID-19?
We're trying to work with with COVID-19. So the funny thing is that we are not directly doing now anything with COVID-19, but people, GeoSpark have seen during the last couple of months a spike in the number of downloads. We used to have on average between 10 and 15,000 downloads per month. Last month only, we had 70,000 downloads.
Oh wow!
So we asked and everything, and apparently people are downloading it because of COVID-19. A lot of people kind of analyzing COVID-19 data, and most of the data is spatial and spatial temporal.
Right.
So they want the system to do that, so they download GeoSpark. So we've seen we've seen a lot of Spark, but now I'm trying to work with domain experts. So there are a couple of epidemiologists and policymakers at ASU and outside. We're trying to look at what are the right questions to ask, because a lot of people are doing work with COVID-19, but because people get excited and all these kind of things, but we need to be careful, because we can misinform the public with the tools we build as computer scientists. So we're looking at aspects of what are the right questions, and then how a computer scientist can help answer these questions, as opposed to, I'm a computer scientist, there is a COVID-19 data, I'm going to take it and visualize it. But this visualization may really, really be dangerous and misinform the public. So we're looking at these kind of questions. So again, how to avoid also data dredging when you analyze COVID-19 data and all these kind of things. So we're looking at these problems.
Great. Thank you very much. Very interesting talk.